For nearly 40 years, planetary scientists had a genuine problem sitting quietly in their data. Everything Voyager 2 recorded during its one and only flyby of Uranus back in 1986 looked strange. The planet's magnetic environment appeared unlike anything else in the entire solar system. Its radiation belts behaved oddly, and for decades, scientists genuinely believed Uranus itself was simply a fundamentally weird planet, until a small team of researchers went back and reanalyzed that decades-old data with fresh eyes, and discovered the planet wasn't actually the anomaly at all. The timing of the visit was, and if you've seen a video calling this discovery terrifying, I want to walk you through what actually happened, because the real story is genuinely one of the more satisfying scientific mysteries solved in recent planetary science. And terrifying, honestly, isn't the right word for it at all. So let's start with understanding exactly what Voyager 2 actually did at Uranus, and why that single flyby has shaped our entire scientific understanding of that planet for nearly 4 decades since. Voyager 2 made its closest approach to Uranus on January 24th, 1986, and to this day, it remains the only spacecraft that has ever visited that planet. No orbiter, no follow-up mission, nothing, just one single brief flyby lasting a matter of hours, as the spacecraft sped past on its way toward its subsequent encounter with Neptune. And it's worth appreciating just how much that single or brief visit actually accomplished despite its short duration. During those few hours, Voyager 2 discovered 10 previously unknown moons orbiting Uranus, along with 2 entirely new rings around the planet, and it captured the first ever close-up images of the planet's 5 largest moons, revealing surfaces covered in impact craters and deep canyons that nobody had ever seen before. And everything we currently know about Uranus's magnetic field, its radiation belts, its moons, and its interaction with the solar wind streaming outward from the sun comes from that one specific brief window of observation. And I think that context genuinely matters, because it means any anomaly or oddity captured during that flyby has had essentially no opportunity to be double-checked or verified against additional visits, unlike planets like Jupiter or Saturn, which have been studied by multiple different orbital missions over the years, giving scientists many separate opportunities to compare observations against each other. And here's specifically what looked so strange in that original 1986 data. Uranus's magnetosphere, the protective bubble of magnetic field surrounding the planet, appeared to be almost entirely empty of the kind of plasma, meaning charged particles, that scientists would normally expect to find there. And at the same time, Voyager 2's instruments detected surprisingly intense radiation belts around the planet, a genuinely puzzling combination, since you'd generally expect a magnetosphere loaded with intense radiation to also be relatively well stocked with the charged particles that create and sustain those radiation belts in the first place. And this specific combination, radiation belts that seemed unusually intense paired with a magnetosphere that seemed strangely empty of plasma, became one of the most persistent, genuinely puzzling mysteries in the study of Uranus for basically the entire time since that flyby occurred. And scientists developed all sorts of theories over the following decades attempting to explain it, with a lot of researchers ultimately concluding that Uranus's magnetosphere must simply behave in some fundamentally unusual, poorly understood way compared to every other planet in the solar system. And it's worth understanding why that specific theory felt so genuinely plausible to researchers at the time, because Uranus was already well known for being a fundamentally strange planet in other well-documented ways. Unlike every other planet in the solar system, Uranus rotates almost completely on its side, tilted at an angle of 98 degrees, meaning it essentially rolls around the sun rather than spinning upright the way Earth and most other planets do, and its magnetic field itself is also dramatically tilted and off-center compared to the planet's actual physical rotation axis, tilted by about 59 degrees and offset considerably from the planet's core, unlike Earth's comparatively simple, well-aligned magnetic field. So given that Uranus was already established as a genuinely unusual planet in these other independently verified ways, it made complete intuitive sense for scientists to assume its strange seeming magnetosphere and radiation belt readings were simply one more example of that same broader planetary weirdness, rather than immediately suspecting the timing of the visit itself might be the actual culprit. And I think it's worth understanding why that specific conclusion, Uranus is just weird, was genuinely a reasonable, defensible position for scientists to hold for so long. Because without a second visit to actually compare against, there was no direct way to know whether what Voyager 2 observed during that one specific flyby represented Uranus's normal typical state, or whether it had simply captured the planet during some kind of unusual temporary condition. And for nearly 40 years, the field genuinely leaned toward assuming it represented Uranus's normal state, simply because there wasn't compelling evidence pointing toward any other explanation. And this is exactly where the actual reanalysis comes into the story, and I want to walk through what the research team specifically did, Because it's a genuinely clever piece of scientific detective work, researchers went back to the original data Voyager 2 collected during that 1986 flyby, and specifically cross-referenced it against independent solar wind activity data from around that exact same time period, essentially checking what the sun itself was doing during those specific few days in January of 1986, and what they found was genuinely revealing in the days immediately surrounding Voyager 2's flyby. The sun happened to be in an unusually active period, and the solar wind, the constant stream of charged particles flowing outward from the sun, was compressing Uranus's entire magnetosphere considerably more intensely than it typically would under normal, average conditions. And here's exactly why that specific detail matters so much. That kind of solar wind compression event is estimated to occur only a small percentage of the time, meaning Voyager 2, through nothing more than sheer, genuinely unlucky timing, happened to fly past Uranus during a brief, statistically unusual period of unusually intense solar wind compression, rather than catching the planet in anything resembling its more typical, average state. And once researchers accounted for that specific timing, the previously baffling combination of an oddly empty magnetosphere paired with unexpectedly intense radiation belts suddenly made considerably more physical sense. That intense solar wind compression event had likely temporarily squeezed and disturbed Uranus's magnetosphere, plausibly flushing out a meaningful portion of its plasma and temporarily concentrating and intensifying the radiation belts in the process. Meaning what Voyager 2 actually captured wasn't evidence that Uranus behaves in some fundamentally bizarre, permanently unique way compared to the rest of the solar system. It was a genuinely rare temporary weather event, essentially cosmic bad timing, that happened to occur during precisely the narrow window when humanity's only ever spacecraft visit to that planet happened to be passing through. And I think that's honestly one of the more satisfying resolutions available in planetary science, because it doesn't just solve one isolated puzzle, it actually helps resolve several separate, long-standing Uranus mysteries all at once, since multiple previously strange observations from that flyby, not just the plasma and radiation belt puzzle specifically, but other related oddities in how the planet's magnetic environment appeared to be behaving too, can now be much more coherently explained once you factor in that the entire visit happened to occur during this brief, unusual period of intense solar wind compression, rather than needing a whole separate, unique explanation for each individual anomaly on its own. And it's genuinely worth understanding a bit more about what solar wind compression actually physically does to a planet's magnetosphere. Because the underlying mechanism is genuinely fascinating on its own terms. A planet's magnetosphere is essentially a protective bubble carved out by that planet's own magnetic field, pushing back against the constant stream of charged particles flowing outward from the sun, and the strength of that outward pressure from the sun isn't constant at all. It varies considerably based on solar activity, and during periods of unusually intense solar wind, that outward pressure increases significantly, physically compressing and squeezing a planet's magnetosphere down into a smaller, more disturbed shape than it would normally hold under calmer conditions. And that kind of compression can genuinely churn up and redistribute the charged particles trapped within the magnetosphere, plausibly explaining exactly the kind of temporarily depleted plasma and temporarily intensified radiation belt readings that so puzzled scientists analyzing Voyager 2's original data for so many decades. I want to spend a moment explaining why this kind of careful data reanalysis genuinely matters so much in planetary science more broadly, because I think it's honestly one of the more underappreciated aspects of how this entire field actually operates day to day. Missions like Voyager 2 collected an absolutely enormous amount of raw data during their flybys, often considerably more than scientists at the time had the tools, the context, or even simply the specific research questions in mind to fully analyze in complete detail during the years immediately following the mission itself. And that means going back decades later and re-examining that same original data, armed with new analytical techniques, additional context from other missions and instruments that didn't even exist yet back in 1986, and fresh scientific questions that researchers simply hadn't thought to ask at the time, can genuinely reveal entirely new insights sitting quietly within data that's been sitting in an archive for decades, without requiring an expensive entirely new mission to actually go collect any new information at all. And I think that's honestly one of the more cost-effective, genuinely valuable things space agencies can continue doing with historical mission data. And it's exactly why NASA and other agencies maintain such extensive, carefully preserved archives of raw data from even their oldest, longest completed missions. Because you genuinely never know when a future researcher, using tools and knowledge that don't exist yet, might go back and find something genuinely significant hiding in it. That's already been sitting there, fully collected for decades. And I think it's also worth understanding the broader practical significance of correcting this specific misunderstanding about Uranus, because it's not purely an abstract academic curiosity either. Scientific understanding of a planet's magnetosphere and radiation environment matters enormously for planning any future mission to that same planet. And there's been genuine growing scientific interest in actually sending a dedicated orbiter to Uranus at some point in the coming years, with NASA's own decadal survey, the document that helps guide the agency's major mission priorities for the following decade, specifically identifying a mission concept called the Uranus Orbiter and Probe as its single top priority for a new large-scale planetary mission. A genuinely significant endorsement that reflects just how much scientific interest has built up around this specific, still largely unexplored planet, and understanding the true typical behavior of Uranus's magnetosphere directly affects practical engineering decisions for a mission like that. How heavily to shield sensitive electronics against radiation exposure, how to calibrate instruments specifically designed to measure plasma density, and what kind of magnetic environment an orbiting spacecraft should actually expect to operate within on a sustained long-term basis rather than during one single brief flyby. And if mission planners had continued designing spacecraft instruments and shielding based on the mistaken assumption that Uranus's magnetosphere is permanently, consistently as unusual and depleted as that one single 1986 flyby happened to suggest, that could have genuinely led to real practical design decisions built around inaccurate underlying assumptions. Whereas understanding that the 1986 data actually reflects an unusual, temporary weather event rather than Uranus's true typical baseline state gives future mission planners a genuinely more accurate picture to actually design around. And I think that's a great concrete example of exactly why getting the history and context of old data right isn't purely an academic exercise. It has real practical consequences for how we actually explore these worlds going forward. And I want to also mention, since we're talking about Voyager 2 specifically, a genuinely important, current, and entirely separate piece of news involving this exact spacecraft, because it's worth understanding where the mission actually stands today, in August of 2026, rather than only focusing on this specific 1986 data mystery. Both Voyager 1 and Voyager 2 are still operating right now, nearly 50 years after their original 1977 launch, making them, by a wide margin, the longest operating spacecraft in human history. And both spacecraft have now traveled beyond the heliosphere, the protective bubble of solar particles and magnetic fields that the sun projects outward, meaning they are the only two spacecraft ever built that are currently operating in true interstellar space, genuinely beyond the sun's direct influence entirely. And here's the actual current challenge NASA's engineers are dealing with in real time right now. Both spacecraft are powered by a radioisotope thermoelectric generator, essentially a device that converts heat from the natural decay of a plutonium power source into usable electricity. And that plutonium source is slowly, steadily weakening over time, meaning each spacecraft loses a small amount of available power every single year. And NASA's mission team has had to progressively shut down individual scientific instruments on each spacecraft over the past several years, specifically to conserve the shrinking remaining power supply and keep the core spacecraft itself, along with a handful of its most essential remaining instruments, operational for as long as genuinely possible. And just this month, NASA's engineering team announced a genuinely clever, resourceful solution specifically to help extend Voyager 2's mission a bit further. They found a way to draw additional backup power from a safety mechanism originally designed to regulate the spacecraft's voltage, and that specific engineering workaround is expected to keep 3 of Voyager 2's remaining science instruments operational for at least an additional year beyond what would have otherwise been possible, postponing the need to shut down yet another instrument. And the team is now planning to implement that exact same kind of power-saving workaround on Voyager 1 as well in the coming months. And I think that's honestly a genuinely inspiring, practical piece of ongoing engineering, ingenuity worth appreciating in its own right. Engineers back on Earth, working with a spacecraft design that's now nearly 50 years old, continuing to find genuinely creative ways to keep humanity's most distant operating messengers alive, and returning real scientific data for as long as physically possible. And I want to bring this all together now because I think the complete and accurate picture here is genuinely more interesting than a misleading claim about terrifying results ever could be. Researchers reanalyzing Voyager 2's original 1986 Uranus flyby data discovered that the spacecraft happened to catch the planet during a brief, statistically unusual period of intense solar wind compression, rather than during Uranus's more typical average conditions. And that single insight has helped resolve several long-standing, genuinely puzzling mysteries about the planet's magnetosphere and radiation belts that had persisted, largely unexplained, for nearly 4 decades. This reanalysis genuinely matters for planning any future Uranus mission, potentially helping ensure spacecraft instruments and shielding get designed around a genuinely more accurate understanding of the planet's typicae. Hell environment rather than an unrepresentative, unusual snapshot, and separately, connected through the same remarkable spacecraft, Voyager 2. Itself continues operating today, in 2026, nearly 50 years after launch, with NASA's engineering team actively finding new, creative ways to keep it collecting and transmitting genuine scientific data from beyond the edge of our solar system for as long as they possibly can. And I think that's honestly a wonderful, genuinely fascinating story about how science actually corrects itself over time, patiently, carefully, sometimes decades after the original data was even collected, rather than the kind of frightening, alarmist framing a misleading video title might otherwise lead you to expect. And it's exactly the kind of story that reminds you why space agencies bother carefully preserving decades-old mission data in the first place, because you genuinely never know when someone is going to go back, look at it with fresh eyes, and finally solve a mystery that's been quietly sitting there, waiting to be understood, for nearly 40 years. If this helped you understand the real, complete, and genuinely fascinating science behind this story instead of a misleading, alarmist headline, hit subscribe. Because we're going to keep breaking down real space discoveries clearly and accurately every single time. See you in the next one.